Hi class, let's take a look at problem 3. So they want us to use the intermediate value theorem to check if there's a root on the closed interval from 0 to 10. Now, just to quickly review the intermediate value theorem, and in this case we're going to be using it to find roots, what the theorem says is the following. And it says that if on a closed interval your function happens to be continuous, there's going to be a point C in the middle somewhere. And in this case, we're going to use that idea to find the roots. Now, what you're going to need is your function to be a single piece on a closed interval, so brackets on the edges, and then we need for it to guarantee the root that your function changes from a negative to a positive value, then there's going to be at least a root. So we're going to have to evaluate the function. Now, for instance, let's take a look at the first problem. And we're going to evaluate it at 0 and at 10. Here, I already did the evaluation previously. And this is what we have. When you evaluate 0 on the function, you're going to get -1. And notice that the function is actually continuous on 0 to 10 since the domain is -1 to positive infinity. Then evaluating it at 10, you're going to get a positive value. Thus, since the domain is from -1 to positive infinity, and you have a continuous function on an interval with a change of sign at the edges, evaluating it at 0 and at 10. Thus, the intermediate value theorem guarantees at least one root, and emphasis, it has to be a closed interval. Now, on part B, I actually provided a sketch with Desmos, and your function happens to be, in this case, one single piece after the values of -1. You can actually see here the root. As long as your function is continuous on, in this case, your interval goes from 0 to the values of 10. Then, and if it changes from sign, in this case, from negative to positive, then the intermediate value theorem guarantees at least one root. So in all the problems as you're checking, you have to mention that at the minimum, the function happens to be continuous on the interval. Also, the change of sign, and then state the theorem that there's at least one root. Okay, for the next part, we're going to solve this algebraically. Okay, so for this portion, in order to find all roots, you need to actually set the values of f of x equal to 0. So in this case, we're going to need to solve. We have that 0, it's equal to, and our function represents the actual log of x plus 1 minus the values of 1. So what I'm going to do is I'm going to be adding the 1 to both ends. So technically plus 1 . So we're going to be adding the 1 . And then we're going to actually have, in this case, 1, it's equal to the log of x plus 1. Okay, sorry about that. I was having technical difficulties. I think it's when I was changing colors. And then the next step is we're going to cancel the log. So we're going to raise both ends to the base of 10. What this is going to do is cancel the log. So you're going to end up with 10 is equal to technically the values of x plus 1. And then we're just going to be subtracting the values of 1. So what this is going to give us is that our x value, so x is equal to the values of 9. The actual root as an x and y, it's going to be 9, 0. Remember that, well, technically this means y is equal to 0. At this point, this is it for the problem. We only have one root, and you can actually see the root on the sketch. So that's a root, 9, 0. Once again, the intermediate value theorem, as long as we have one piece, and your function happens to be continuous on a closed interval, it guarantees at least a root. That means that you could have more than one. So that's actually it for this problem. Let me display it again, the actual process and the solving.